Welcome back, everybody. Today, we're going to continue our discussion of these oblique shocks, expansion compression fans, and we're going to finally really describe in detail what's going on the outside of a rocket nozzle, particularly when you're between the second and third critical. And then, and we'll talk about a couple other external flows when you have a high Mach number. And then we will transition to talking about Fanno flows, which are kind of duct flows where you have friction, wall friction effects. Okay, so here, let me start the screen recording here. So last time, we talked about Prandtl-Meyer and finished fleshing out those ideas where we had, expansion / compression fans, which sort of were an isentropic mechanism. For flow direction changes, as well as pressure drops and pressure increases, right? And so we fleshed out the math and the arguments behind those phenomena, and so now we can talk about over and underexpanded nozzles. So what we'll start with is an overexpanded nozzle. And what that means is that you're between the second and third critical. And here I'll just sort of draw the pressure curve here, where this is the throat, just so you have it, let's say this is the exit here, and then this would be the pressure over the upstream stagnation pressure PT. And if you'll remember, it drops down to the throat, and then we're continuing in this direction, and we go all the way to the exit, where we're right at the third critical, and then say we're at a point where you have some sort of shock process that occurs there and goes up to here, and let's say that's the second critical, the second, and the third critical would be right here. So we're somewhere in between these two pressure levels here in this sort of red scratched out region, okay? Which I said would result in shocks outside the nozzle, and now we're going to kind of examine that entire structure. Now that we had the oblique shocks, we started the last lecture and we saw that structure, and now we're going to go beyond that and see the role that the expansion fans play in that process continuing after the nozzle exit. So let's go ahead and draw what's going on here, and this will be a kind of a difficult drawing to do. Hopefully it'll be intelligible by the end here. So what I'm drawing here is literally the nozzle exits, and then, like I did before at the start of the last lecture, I'm going to draw the center line here, which acts as a line of symmetry, but you can actually treat it in your head like a physical boundary. So at station 1. We have the flow we're making a 1D assumption, so the flow is essentially traveling, parallel to the center line going outwards. And we talked about that in order to reach this ambient pressure, because that ambient pressure is higher than the pressure at station 1, which would be the pressure if you followed the third critical line all the way to the exit, right? Because that pressure is higher, we need some sort of shock condition to reach that pressure boundary condition, and that shock is the oblique shock that forms that kind of this angle here. And we'll draw it on the top 2. Okay, and then once you go through that oblique shock, you change direction. You're going like this direction at station 2, but that region in region 2 has the same pressure as the ambient pressure, right? But that flow direction cannot continue because it will run into the center line, and it has to sort of, by symmetry, would have to change direction and be parallel to the center line again. And so what happens is you get another oblique shock. Looks like that. Okay, and now in region 3, the flow is parallel to the center line, but now in region 3, the pressure is too high. Okay, so it needs to drop through some sort of mechanism to be the same as the ambient pressure again. And so that was where we left off at the start of the last lecture and went into this discussion of Fanno expansion fans. And so what happens here is exactly that. You have a set of expansion waves that changes the direction of the flow again, but makes the flow have the proper pressure. Sort of forgive me if I go silent while drawing here. This is where the drawing really gets difficult. So these are all the sort of expansion line fan lines coming from both sides. And so when this flow goes through these expansion waves, it turns in this direction downwards, right? Because it's like when you would go off of a flat surface and turn downwards, and you get that Fanno expansion fan. It turns down through the expansion waves. So now this is like region 4, and then we have a new kind of free boundary that looks like this. Okay, parallel to that flow direction. Here, I'll change it. I'll make it a little bit more shallow just to make the drawing a little bit easier to do. Probably should be at a little bit of an angle though. That looks good. And then we'll make sure that this line that we draw here is parallel to that dashed line. Okay, and so all these expansion waves are going to go kind of the way you draw them is to continue until they hit that free boundary. And then we have this is where it gets a little interesting, is once again we have this problem where the flow on both sides, so here it's parallel, it's diverging now, right? That's a little bit exaggerated, but the flow is diverging from the center line, which that violates conservation of mass. You can't have eventually you're going to vacate that space, and the flow is going to want to turn back inwards. So you actually get the flow has to turn through an additional expansion fan to change direction, because from here it could, if it went through another sort of, let's say, an oblique shock, it would turn further outwards. So to turn back in towards the center line in region 5 here, it goes through this expansion fan. And so now you have a pressure. So remember, in region 4, the pressure was balanced with the ambient pressure, but But now in region 5, the pressure has dropped below the ambient pressure again. So now you're almost at the same spot you started in region 1, in region 5, where your pressure is lower than what it would be to meet the pressure boundary condition with free space. And so now it has to go through another compression event, in this case an oblique shock, that essentially is represented by a bunch of compression waves, like a Prandtl-Meyer compression fan that coalesces to form an oblique shock here, at least what I've drawn. And then at this point the process continues. So where 6 goes like this, and then 6 has to go through another oblique shock to become parallel, 7 like this, and then we have an expansion fan, and then it repeats. So let me go ahead and sort of do my best here to draw the mirror image on the other side here. So these guys continue. And then they all form that's so bad. Here, let me erase this. It's actually easier if you kind of draw it on the bottom and then go back up in reverse to make it work. Like I said, apologies for for just going silent here. Trying to make sure that this drawing is intelligible at the end of all of this. So there's another free boundary here. This flow direction in region 6 should be parallel to that boundary. This has to go through another shock region that's parallel. And this expansion fan. It's there, and those interpenetrates, and you get this process. Okay, that repeats. So this thing here, this is the expansion fan. Just make sure everything is labeled here. And then this is a Prandtl-Meyer compression that coalesces to an oblique shock. These guys are just straightforward oblique shocks. Okay. And like I said, this process repeats, and you might be familiar with the structure here. This is what you would call a mock diamond. So this is like a mock, or you might have also heard it be called a shock diamond. So if you ever see a rocket engine operating near sea level, usually the pressure outside the engine is too high, but you don't want shocks in the engine nozzle. So they at sea level, engines actually will operate in between the second and third critical because they want their most efficient portion of the flight to be some large time when they're going up through the atmosphere at a lower back pressure, and then eventually once it gets high enough, the nozzle will be underexpanded, where the pressure outside is actually lower than third critical, and we'll look at that structure in just a moment. but yeah, so you get this mock or shock diamond structure that continues, and this is actually something that you can observe quite readily, on tests, and also in rockets that are, like I said, operating. They're just taking off, or in this image on the bottom left, this is a rocket motor on a test stand, and you can see that mock diamond structure. I mean, it's pretty strong, and repeats for many cycles before it sort of dissipates into, essentially you get these shear flows that cause turbulence to come into play, and the structure deteriorates as you move down the stream. But this is a test stand where you can see that structure persistent. There's a missile or rocket on the top left that has a long repeating mock diamond structure. It's probably operating closer to sea level. And then on the right, you can see a bunch of engines with a really, really sharply defined, at least first cycle of the mock diamond structure. I think that's a Blue Origin launch. And then one of my favorites is actually Starship when it launches. The flow from all of the Falcon 9 engines is sufficiently parallel, and quasi 1D, that when they coalesce to form that huge plume, exhaust plume of the Starship, right when it launches, you get this mega mock diamond. It's just like a mother of all mock diamond structures, from all these engines working together. So these images are just so cool to look at. But you can kind of, now that you've gone through and really analyzed how these structures come up through these expansion and compression processes, you could go and look at these diagrams and draw the angles of the oblique shocks, and whatnot, to see very clearly what's responsible for this structure. So, like I said, very, very fun to look at. And there's all sorts of beautiful images of these things. Now that we have so many public rocket launches, there's some photographers that can go out there and get some good images. So I encourage you guys to take a look at these for the various SpaceX and other company launches. But so in general, what's happening here is that you have shocks, compressions, and expansions to meet pressure or flow direction boundary conditions. Okay, so and this is sort of the key, and I actually encourage you to, and even though I had said this as we worked through the diagram, I encourage you to sort of pause the video, and then at every point I want you to take the pressure at every station and ask yourself what is it relative to the back pressure or the ambient pressure, or P ambient. Is it larger? Is it smaller? Is it the same? But we'll go ahead and work through it now. So at pressure 1, because we're between the second and third critical, that is lower than the ambient pressure, right? So what's happened here is you followed this pressure curve down along the third critical line all the way to the exit, but the pressure there is lower than it would be for you to have a shock right at the exit to meet that pressure boundary condition. But it's still not low enough for you to have isentropic flow continue outside the nozzle and basically get this straight 1D flow out of the nozzle. And so you get this case here where P1 is less than P ambient, so that's between the second and third. That's why to say once again, when we call it over-expanded, so meaning that the pressure the nozzle has decreased the pressure of the flow beyond what it would have to be to meet that exterior boundary condition. So we call it overexpanded. And so then it goes through that oblique shock to meet that pressure boundary condition. So P2 is equal to P ambient. P3 goes through another oblique shock to meet a flow direction boundary condition. An oblique shock will increase the pressure. So P3 now is too high. It's greater than P ambient. P4, we went through an expansion fan to meet the pressure boundary condition, right? So that means that P4 is equal to P ambient. And then we have P5 was trying to meet a flow direction boundary condition with the proper process for that is an expansion fan. And so it goes through an expansion fan to do so, which makes P5 less than P ambient again, since the pressure drops through an expansion fan. And then we have a Prandtl-Meyer compression that brings you back in line with the pressure boundary condition at P6, where P6 is equal to P ambient. Okay, and then P7, you're going through an oblique shock again to meet a flow direction boundary condition, and so now you're greater than P ambient again. But in the process here, like 1 is mapped to 5, 3 is mapped to 7, and it continues. So every time a flow direction boundary condition is being satisfied, that sort of screws up your pressure boundary condition, and then you have to go through some other mechanism to satisfy the pressure boundary condition, and then they're passing each other off. And then, eventually, at this free boundary where the flow is sort of parallel to the external sort of quiescent fluid, let's say. Eventually, that there's a shear force that's at play there, where you have this really fast flow from the rocket exhaust that's directly sort of running against a quiescent flow. Let's call it quiescent, even though it isn't necessarily true. And that shear at that boundary causes a turbulent cascade. So eventually, that is not a stable fluid structure. We have really fast fluid running by or two fluid flows that are running across each other. You get the vortex generation, and that sort of sheet collapses, and you get this turbulent cascade that dissipates the energy in the wave structures, and so the exhaust kind of just becomes this like column of turbulent air or exhaust, and so that's what causes the process to eventually break down. Okay, so let's also just talk about underexpanded flow. So now underexpanded. So what's happening there is we're below the third critical, so we're like somewhere down here for the ambient pressure. And so what's happening in that case is really you're just essentially just starting at 0.3. Right, so at 0.3, our pressure has gone through right. Our pressure at 3 is too high, and so we need to go through some sort of expansion. So the reason why they call it underexpanded is because you followed this third critical pressure line to the exit, and it's still not a low enough pressure to meet the boundary condition. So you need to go through a Prandtl-Meyer expansion right as you exit the nozzle. So, and what do I mean by start at 0.3? Well, I'm just saying, what I mean by that is that the sort of external flow structure is the same as though if you started at 0.3. So in this case, we have much the same diagram. We have a flow coming out parallel to the center line. And then P1 is greater than P ambient. The nozzle wasn't able to expand the flow enough or lower the pressure of the flow enough to make that boundary condition match. And so what you end up with is an expansion fan. At this exit. Okay, and then the flow turns away from the center line. Make that a little bit more dramatic. And now the free boundary is going outwards. And you can actually see this if you look at rockets operating really like a long lens photograph, say, of a rocket that's operating really starting to leave the atmosphere. You can see that the exhaust plume gets extremely large. It's like a massive bell shape, and it's because it's going through that expansion right at the exit, and so the plume is spreading out quite large. And so you have two here, and then these expansion waves continue. You can draw them that way. And now, just like before in station 2, we need to turn back inwards through another expansion to be parallel to the center. Apologies for the messiness of the drawing. But it's, like I said, it just kind of, the process just starts over. So these waves sort of, quote unquote, reflect off the free boundary there and change the direction of the flow to be back towards the center to meet the pressure boundary condition after the expansion. And then the process repeats: compression to meet a flow direction boundary condition, and so on. Okay. Okay. Hopefully that's understandable. Okay, so let's talk about one way to construct these diagrams. I don't think that it's a useful, let's say, like almost like a mnemonic device, what we're about to say, but it's not necessarily a very good way of physically understanding what's happening. But we should make a note about it. So let's talk about what we might term as reflections. So if you looked at the first diagram, it's a little bit easier to do here. You may have noticed that basically at the free boundary, it seems like this oblique shock is reflecting off of the center line and going down here, and then it's also reflecting off of the free boundary. Even though it seems like even though it changes character into an expansion wave, it's reflecting off of that. And then again here, all of these expansion fan waves are reflecting off the free boundary right here. And then the oblique shock that they coalesce to form is reflecting off of the center line. Okay, so it seems like there's reflections happening here, but in reality. So you can look at it like this. You can say reflections off free boundaries cause the wave to change character. So what do I mean by that? What I mean is that whenever a reflection is occurring down here off of this dashed line, the wave turns from an oblique shock to an expansion, or from an expansion to compression. Okay, so they're changing character from expansion to compression. And then reflections off solid boundaries preserve character. So I said when we first started talking about these structures, I think in the last lecture, the center line, essentially you can think of it as a physical wall. And the reason why is because you need that flow symmetry across the center line. And so because you can treat it like a physical wall, it behaves like a physical wall. And all of these reflections where, say, the Fanno expansion waves and the oblique shocks are reflecting off of that center line, they are keeping their character, right? Like the oblique shock is not changing. Is not turning into an expansion. It's bouncing off as an oblique shock. Okay. So, and I should also say we're pseudo-solid, because the center line is not a solid boundary, but it's like a pseudo-solid boundary. But the reason why I'm presenting this as like a type of mnemonic device to help draw these diagrams, instead of thinking of that as what's actually physically happening, is that they're not actual reflections. And this is a real pitfall that people fall into, where they're looking at these structures and they assume that, for instance, that the incident angle theta incident is equal to theta r, and that is not true. So, like looking at this transition from 4 to 5 here, these two angles are not the same. Okay, there's some sort of rotation of the shock according to the pressure and flow direction conditions that requires that will require a different sort of shock angle. Okay, so just keep that in mind. So if you're asked to analyze a flow out of the exit of a rocket nozzle, you can proceed through this process, and then if you're like at station 4 and you're thinking, I don't understand which direction I want to turn here, or this or that, you can kind of look at what's happening at the center line and at the free boundary and be like, I know that these Fanno expansion fans must sort of change character at the free boundary, and so I know that it's going to be a compression between station 5 and 6. Okay, just a way to help you draw the diagrams, but definitely not physically rigorous. Okay, cool. So that's sort of a detailed discussion of over and under expanded nozzles. The next section that we want to talk about is supersonic airfoils. You know what? I should have been its own, sort of highlighted as its own section. So one thing that you may have observed when looking at most airfoils that you see deployed in aviation is that subsonic airfoils have rounded leading edges. And that's because they operate at speeds or Mach numbers where the flow is almost perfectly described at least in the bulk flow, by Euler's equation. It's like ideal flow, and that's the sort of ideal airfoil shape to maximize lift and minimize drag in that scenario. But if we have one of these blunt leading edge airfoils in a supersonic flow, what we've learned, and we'll just say n be greater than 1 here, what we've learned is what's going to happen here is you're going to end up with a detached shock that's sort of a normal shock directly upstream of the object, and that you're going to have sort of this subsonic flow then on the other side of the shock, and that shock will bring you a lot of losses. So detached shock corresponds to big losses, and that's because since the shock is approximately normal directly upstream of the airfoil, it's a very strong shock. And strong shocks result in larger losses. Okay, so supersonic airfoils, and this is where another thing you might have observed when you look at aircraft that are meant to travel at supersonic flight speeds, is you might have noticed that they have very sharp leading edges. So supersonic airfoils have sharp leading edges to mitigate this shock detachment issue. Okay, so the limiting case is like a flat plate, okay, which is actually very useful to analyze. So like imagine you have, some sort of flat plate here, a literal flat plate airfoil has this angle of attack here, alpha, and you have some sort of incoming flow, M1, which is greater than 1, it's supersonic. And the question becomes, okay, what happens? What happens on the top and bottom of this? Well, we know that there's going to be some sort of flow direction boundary condition, right? Because the flow can't just continue over the top edge of this airfoil straight, or else you would have a void kind of in in the shadow of the airfoil, right? So that's not that can't be there. So it has to turn downwards to we'll call this region 2 to be parallel with the airfoil, and that turn downwards is going to be, you can think of it this way. I'll tell students, is the flow turning down into empty space? In which case, you can think of it as an expansion process, right? Like the pressure ought to be lower if the flow is sort of expanding to fill empty space. So the top edge, you're going to see a Prandtl-Meyer expansion fan, okay? And then the bottom edge, the flow is essentially running into a wall before it turns direction, and so it's compressing. So the bottom flow direction, on the bottom edge of the airfoil, let's call it region 3. To meet that the flow direction boundary condition, you're going through a compression-like process. And then once you return to the free stream, we'll do like a dotted line here. That's horizontal or parallel to the initial. But once you go back to the free stream, we'll call that region 4, and we'll call this region 5. The flow direction has to be parallel again. Okay, and so we've talked about how center lines, they're like hard walls. So the flow direction, the flow in region 2 is running into that center line hard wall, and it's compressing, and so you have a oblique shock forming on the top edge in that case, and then the flow on the bottom is going through an expansion fan to meet that flow direction boundary condition. Okay, and so like your boundary conditions essentially are like that V4 is equal to V5, right? So you can have some sort of unstable shear. And then also that the pressure at 4 is equal to the pressure at 5. And then to actually solve for everything here properly, what you have to do is you have to, find the solution for all the shock angles and everything through trial and error. Some sort of iterative process, iterative solver. If you want to solve for all 4 of these conditions for a given M1. And so we actually can solve for the lift per unit span here. So that's if we. So to be clear, the trial and error process here is if we wanted to find what the flow conditions are downstream of the airfoil, but that's not actually necessary for getting the pressure distribution across the plate, because all we need is that flow direction boundary condition that we're trying to satisfy when we transition between the free stream upstream of the airfoil in regions 2 and 3. And so we can figure out what the pressure in regions 2 and 3 are by using essentially the Prandtl-Meyer function that we derived, I think, what was it at the end of the last lecture? Oh yeah, nu. So, and also the oblique shock relations, or doing some oblique shock analysis, I should say. So let's solve for the lift per unit span. Solve for lift per unit span. So suppose M1 is equal to 1.8, and your angle of attack alpha is 5 degrees. And we'll also set the P1, which is also it's just your ambient pressure, to be 0.4 bar. Okay. And so now the flow over the top experiences a 5-degree turn Prandtl-Meyer expansion. Flow over top, 5-degree, I'll just say nu equals 5-degree PM expansion. And it started from m equals 1.8, right? So nu2 should be equal to nu1 plus some sort of increment in nu, let's say. All right. And so nu1 was what you get when you plug in m equals 1.8. So this is 20.725 degrees. So just to remind yourself, that's nu of m1. And then we want to add the required change in flow direction from our angle of attack, okay? And so to figure out what the Mach number is at station 2, we take this total angle that we just got out, which is 25.725 degrees, and we look at that in the tables to find that M2 is equal to 1.976. And then also from the tables, isentropic relations, we can see that the ratio between the static and stagnation pressure at this Mach number is 0.1327. Okay? So we keep that, okay? So we have that, we're sitting fine with that information. Now let's look at the flow under the airfoil. So flow under, we are going through, we're being deflected 5 degrees by an oblique shock, right? So what you need to do is you need to look at a chart of deflection angle, shock angle, and an upstream Mach number. In this case, it's in Zucker and Biblar's. This is in Appendix D. Okay, so for a Mach number, upstream Mach number of 1.8, and a deflection angle of 5 degrees, you'll see that theta is either 38.5 degrees or 83 degrees about. And so the question is, okay, which one of those is it? And remember, we talked about this for external flows. The oblique shock that you're going to get is always, of your two options, the weak or strong is going to be the weak one, because the pressure gradients aren't strong enough to drive this 83 degree shock. So you're going to ignore that one, pick 38.5 degrees. Then you can calculate your Mach number, your upstream Mach number normal to the oblique shock, which is just n1 sine of your shock angle theta, which in this case ends up being 1.12. And then use that with your shock tables to find that P3 over P1, the change across the shock, is equal to 1.2968. Okay, and that is in Appendix H, those normal shock tables. Okay, and so like from there we know that P3 is just going to be 0.5187 bar, and we can essentially, the pressure is going to act are perpendicular to the cord. So the force of pressure is going to be in that direction. This line is parallel to the direction of the airfoil, and then this angle here is alpha. And if we're interested in this force of lift that's directly upwards, right? Well, we know that this is also alpha here. And so we can calculate the force of lift as the pressure difference between region 3 and 2, above and below the airfoil. We multiply that by the cord area, and we get cosine alpha, or multiply by cosine alpha. Okay, and so what you end up getting in this case is 4.26 times 10 to the 4 newtons per unit span. Okay, so that's how you would do that lift calculation. A flat plate is it's interesting that you can actually get some lift out of a flat plate here, but a more practical design would be something called a double wedge. So the double wedge looks like this. So let's say you go like that, and then, oops. This is a little tricky because that side would be parallel to that side. Okay, so in this case you have expansion wave on the top, oblique shock on the bottom, another expansion wave because the flow's turning down into free space more. Same thing on the bottom, you get an expansion wave here. And then on the trailing edge on the top, you get a shock, and then on the bottom, you get a compression. And the flow goes out like that. Okay. It's interesting for this double wedge structure. The waves that you get on top and bottom are actually alpha dependent. So if let's say your angle of attack is more shallow, like this case where it's still, geez, I'm drawing these so terribly, where it still might be very, very slightly positive. Flows like this direction, but you actually have a oblique shock on the top and bottom, then 2 expansion waves, and then another 2 oblique shocks on the trailing edge. So I just say they're like alpha dependent waves, and that is just a matter of essentially it depends on your oblique your angle of attack. There's a direct relationship between whether or not you have a expansion or an oblique shock on the top, and I think you do that. Go through that in detail on your homework, and so we won't go over it. We won't do it in detail right at the moment. You can also have biconvex airfoils, which based on the name you can guess, it sort of has a sharp leading and trailing edge, but it's a gradual surface. Typically, you end up with this sort of shock structure, and then along the actual surface of this airfoil, you get expansion waves as it changes direction, little by little. So you say expansions all across surface. So those expansion processes are probably a little bit closer to the, let's say, isentropic Prandtl-Meyer expansion that we use for analysis, because they're not all happening in this sort of single change in direction. But you can also have triangular airfoils, which are just have the top of the double wedge, but a flat bottom. And same thing, you have a Prandtl-Meyer expansion here, and then typically you just got 2 shocks on the trailing edge. Okay, those are just some general shapes that you'll see. Another interesting one that I wanted to show you was the Aerospike Nozzle. It's an interesting nozzle idea. So I think I mentioned this fact where the rocket nozzle is going to, because the rocket nozzle is going to perform differently depending on what your atmospheric or back pressure for the nozzle is. It's going to operate at a different efficiency depending on what altitude the rocket is at, right? So at sea level, you'll be overexpanded, and then at the higher altitudes, when you're starting to transition into orbit, let's say, your engine's going to be underexpanded. So there's inefficiencies associated with both of those. Ideally, you want it to be operating at the 3rd critical. That's the most efficient operating condition, where the flow proceeds out of the engine without any sort of shock structures that cause loss. And so one idea to mitigate this was the Aerospike or plug nozzle. So one thing you might have thought of to deal with this operating regime issue is that you're like, well, why don't we just vary the nozzle exit area? And then that way the nozzle is either expanding the flow more or less, depending on what altitude you're at. But that's not practical, especially for a rocket nozzle, because the forces at play don't play well with moving mechanical parts. And so because that sort of variable dimension nozzle is not practical, and those do exist, by the way, for some jet engines. They have adjustable nozzles, but for rockets, it's not practical. So what they do is they sort of sought an idea that leads to the same effect. And so what this looks like is you would have this sort of drawn simply. It's like a simple kind of wedge like this. Okay? And then you would have these thruster modules that are themselves sort of a converging, diverging rocket engine that's firing its exhaust at an angle parallel to the top of the wedge. And what happens is this gradual change in direction, you always have a free boundary on the outside here. Okay, and then as the flow turns, so the flow on the inside is turning through these sort of very weak oblique shocks as it compresses in, where it's like something that, you know, in the limit is you're doing Prandtl-Meyer compressions on the inside, and then on the outside you're doing, you know, Prandtl-Meyer expansions. So, you know, there aren't any structures occurring here to change for this flow direction change that are causing a huge amount of losses. And then by the exits, you have some sort of, like, you know, small gas flow out of the engine there. And by the end, the flow kind of coalesces down these channels here, and it's all parallel to the, you know, all of your thrust is, it's parallel to the direction that you would like it to be, right? And so these are free boundaries. Oops. And because those are free boundaries, so this would be the operation at low altitude. Okay, but that same setup at high altitude your free boundary expands outwards, right? So your free boundary kind of comes out this way, and you'll have a, you know, big Prandtl-Meyer expansion fan right off the edge of the thrusters. And you end up with this very large sort of, you can think of now as, you almost have like these two sort of bell-shaped, bigger regions for the flow to be more efficiently expanded. So it's like the nozzle expansion is continuing beyond those thruster modules, and your overall nozzle is huge now, as you're able to expand the flow more at the higher altitudes, and you can get closer to something like third critical operation coming out of the bottom of this large structure here, flow structure here. So your free boundary expands outwards. It's basically like a variable diverging section. Okay, so that's the idea behind the Aerospike nozzle. It's like essentially utilizing this idea of the free boundary expanding notice that it functions just like a variable nozzle exit, so that you can continue to expand the flow when you get to those higher altitudes. Okay, so that's the idea of the Aerospike. This qualitative understanding that we have of these external flow structures lets us to explain what's going on with the operation of this device, which is a very interesting device. But that's sort of a good way to wrap up our discussion about these external flows, particularly these nozzle exhaust. And you'll have some homework problems that deal with these topics in detail. But now I want to switch gears, and I want us to talk about internal flows again. In particular, flow with friction. Which is termed Fanno Flow. Which is named for a man named Gino Fanno, an Italian. And he has an interesting story as well, much like the other people that we've encountered so far. His name is Gino Fanno, and he was born in 1882 and died in 1962. He was a Jewish man who lived in Italy, okay, during this time. And so, anti-Semitism in Italy was getting very intense, even in the very early 20th century, much long before World War II. And he actually fled Italy for that reason, for Switzerland in the year 1900. And then he pretended to be Roman Catholic. And so there he got his master's degree, and he returned to Italy, to his homeland, to obtain his PhD, and he did eventually get his PhD in 1935. And he was doing very well for a short period of time, a few years. He was doing work in his area of competence. He was well respected, but in 1939 he was stripped of his PhD in fascist Italy due to his Jewish faith, and so he made it through World War II, but after the war he was only able to find work in agriculture. And essentially, for his lifetime, the results that we're about to discuss that have become very important to internal flow analysis were not acknowledged during his lifetime. He actually, the flow setup that we're going to study here was proposed in his master's thesis, and so it was only after his death that the value of his work was realized. And unfortunately, it was the anti-Semitism that he had to face in his mother country prevented him from being productive, in his later years. So a bit of a bummer deal. But in honor of Mr. Fanno, Dr. Fanno, I should say, we'll proceed and hopefully describe his ideas with precision. So, to start, we're going to isolate the effects of friction. And what I mean by that is, we're back into duct now. We're not talking about external flows. We're going to assume that the flow is steady. We will assume that it's 1D. We'll assume that there is no heat or work being done. We'll assume that there's potential energy gravitational potential energy is negligible, and we're also going to assume that the area of the duct is not changing, so constant area duct. Okay, so up until now that would basically make our problem completely boring, but we're going to allow friction into the equation when we talk about momentum conservation. But first, we're going to talk about mass conservation continuity. We know that for this setup, we're going to have rho AV is going to be a constant whenever we have 1D steady flow. This is the case. But So we know that's true. But A is also constant. So basically, rho times V is itself a constant. And what we do is we define G as rho times V, and we call this the mass velocity. Okay? So it becomes a useful quantity when you have a constant area of flow. So if we look at the energy equation, we have said that this is adiabatic with no work, right? That was one of our assumptions. So that means that our total enthalpy, which we can express as h plus v squared over 2, that thing is constant, right? Just by the energy equation. And we can rewrite this in terms of the mass velocity in the following way, where we have g squared over 2 rho squared, right? We just basically multiply that term on the right by rho squared over rho squared. And then that thing itself is equal to a constant. So what we can do is we can create this these Fanno lines. And what I mean by that is we can plot these lines of constant h plus g squared over 2 rho. And analyze the flow that way. So let's do an HV diagram. So h versus velocity. And we know that sorry, not versus velocity. That would be that's specific volume. Apologies. H versus specific volume. Our total enthalpy HT is constant, of course. And then we will draw these lines here. So these lines that I'm drawing right now are lines of constant G, which is constant for a given Fanno process, right? Due to mass conservation. So this is a G constant line. As you move inwards in this direction, this is the direction in which G is increasing. Okay, and if we were to, at the same time, draw lines of constant entropy on the same diagram, what we would get is lines that look like this. Where S is increasing this way. Okay, and I'll go ahead and label this as S constant. Okay, and then these black lines here, we call those Fanno lines. Each one represents a specific Fanno process because G is constant. Okay, and then if we do this, we also draw the properties H versus S, which is to be frank the more important diagram. So you can look at the diagram on the left and kind of imagine if now all of those lines of constant S that we drew with the dotted lines were just the x-axis and they were flattened. You can see that the Fanno lines now kind of have this general shape where they're like a parabola kind of on its side. Not exactly a parabola, of course, but sort of reminiscent of that. Okay, so each of these are now the Fanno lines. Okay, and so and like I said, over this is in reference to the diagram on the left. That's the high G Fanno line, and then you have low G or low mass velocity Fanno line out there. Okay. And so now this is where you want to, take a step back and kind of discuss what's happening on these Fanno lines. So, we're fixing, let's say we fix G and H. Okay. So, what should happen? Do fluid properties change when friction is present? And the question and the answer is of course, right? We have some sort of frictional losses, right? So when friction is present, there are losses. So, heat is being, generated at boundary, say, by some sort of entropic processes, which is like this fast moving channel wall next to the flow, right? So the fluid density is going to decrease, or in general, or you can think of it this way. It's better. I think it's more intuitive to think of it this way: is that you have you're losing pressure, right? So if the pressure is what's driving the flow, some portion of that pressure head is being lost to losses from the friction at the walls of the duct or pipe, and so you are eventually dropping pressure, and your fluid density is decreasing. And because G is constant and your pressure is decreasing, it actually causes the flow to speed up. So this is the real, to me, extremely unintuitive thing is that for a subsonic flow on a Fanno line, when let's say you're in a duct and you include frictional effects, your flow starts to speed up as it proceeds through the pipe. It doesn't slow down due to the introduction of friction. Very, very, very unintuitive. But this is because you are losing pressure faster, and the fluid density is decreasing along with that pressure drop, which requires V to be higher because we have this G or rho times V is equal to constant fact. Okay, so let me write some of that down. So the heat is being generated at boundary and lost. Rho goes down, which implies that V goes up, right? Because G is a constant. Okay? So let's sort of draw a single Fanno line and observe what's going on here and on an HS diagram. So we have our total enthalpy, HT, and our Fanno line looks like this. Okay? And so let's look at state 1 at one point in the duct and state 2 some point downstream. And why did I draw it this way? Well, we know that as as the flow progresses down this duct, there's entropy production, right? And so, some of our energy that's driving the flow, wrapped up in the pressure gradient, say, is being converted into entropy, and so or is causing entropy production is what I should say, and so the entropy must be increasing in the flow as you progress downwards, and so the entropy is the flow on the top branch is sort of progressing to the right always, right? And we can draw the pressure contours on this plot. They sort of look like this. Let me draw them in a different color. Draw them in blue. So the pressure contours are kind of at this angle here. And so these are like the pressure contours, and the increasing pressure is in that direction. Okay, so the pressure is dropping as we move from point 1 to 2, and then you can see here something interesting happens. So eventually we're going to hit a point here where the entropy is maximized, right? And so what happens there, right? Can the flow proceed, continue to proceed in a duct that has friction and entropy production if G is required to remain constant and seemingly you can't increase the entropy anymore? That's interesting. So keep that in mind. We'll talk about that in detail in just a moment. And so, we could also have, the case where we have, let's say this is 3 and 4 here. We know that here, the flow is going in that direction, right? Because the entropy must increase between two points on the same process. So now you can see that, there might be some fundamental differences between what's going on above the limiting point, what we'll call the upper branch, and what's happening below the limiting point, which we'll call the lower branch. So let's actually go through a table and talk about what's happening on the different branches, right? So we're going to look at various properties, and we're going to fill in whether they're going up or down on the upper or lower branch. So on the upper, this is the 1 to 2, and then the lower, which is represented by 3 to 4 on the diagram. And we want to look at how the enthalpy is changing, the density, the velocity of the flow, pressure, and the total pressure. Okay, so on the upper branch, we can see just from the diagram that the enthalpy is going down. We also know that the density is going down through the reasoning that we had before, and the fact that the pressure is also going down. And then because G is constant, this requires V to go up or to increase. And we also know that PT must be going down. And the reason for that is because we know that PT2 over PT1 is equal to e to the minus delta S over R, right? We don't have any heat in this case, so heater works. So this equation still holds, and we know that there must be stagnation pressure drop as we proceed along this. But on the lower branch, it's a little different. So H is going up, and we also know that if we continue to draw in these pressure level sets, it would be clear that, and it is clear just from those two that I added, that the pressure is actually going up on the lower branch. Same with the density, and then because the density is going up, the velocity must be going down. Okay, and then the total pressure, or the stagnation pressure, is also going down on the bottom branch because you still have entropy production. Okay, so that's interesting. So the flow is speeding up on the upper branch and decreasing on the lower branch. Okay, so the question is that we sort of alluded to just a moment ago is what's happening at the limiting point, right? What's happening where at that point where we hit the point where we're at the on the line of constant G where the entropy is maximized. Okay, so we know that the total enthalpy is constant. So if we take the total differential of this, we get that dH plus V dV is equal to 0. Okay. We also know that rho V is constant. So if we take the total differential of that, we get V d rho plus rho dV is equal to 0. And we get that dV is equal to minus V over rho d rho. And if we put these two guys together, we get dH is equal to V squared over rho d rho. Okay, so remember, or recall I should say, that TdS is equal to dH minus V dP. That's just the fundamental thermodynamic relation, first and second laws put together with the definition of enthalpy subbed in. If we sub this into that relationship, what we get is that TdS is equal to V squared d rho, so I should write there, du rho over rho minus dP over rho. Okay. So now let's look at this relationship at 2 points sort of above and below the limiting point. So what I mean is, so we're looking at, so we're going to surround or be in the neighborhood of the limiting point. So on the diagram, let's say we're looking at state A, that's sort of directly above the limiting point, which I'm representing by a circle here, and then something B. So looking at this diagram, you can see like A and B are where I'll put these red dots here, okay? So we're looking at around the limiting point. We know that we can write out this equation where it would be T times delta S AB is equal to V squared times delta rho AB over rho minus delta P AB over rho. Now we know that because it's a limiting point and it's the entropy is tending to a maximum, that very close to that point, the change in entropy between A and B is basically the 0, right? So we can sub that in to the equation above, and what we get is that V squared times the pressure, or sorry, times the density change from A to B is equal to the pressure change from A to B. And what does this look like? Well, this is like V squared is equal to the change in pressure divided by the change in density when the change in entropy is really, really small, right? Well, let's take the limit of that. And what you see is that the limit, if we look at that in the limit, that's just dP d rho at constant entropy. And that's A squared. Okay, so this analysis just showed us that V is the sonic velocity at the limiting point. So the upper branch is subsonic. Lower branch, that is upper branch being above the limiting point, lower branch being below the limiting point in that diagram, is supersonic. Okay, And so if you're in a duct that has friction and you're starting out with a supersonic Mach number, as you proceed, you'll get slowed down until you reach m equals 1, at which point you can't there can't be any more entropy production while preserving conservation of the mass. Okay, same as if you enter that duct with Mach equal less than 1, then your flow will be sped up until you hit Mach equal 1, and then this whole idea of not allowing any further entropy reduction, it basically stops you there. You can think of this, and in fact it is called friction choking, but it's a little bit different from the choking that we've talked about in nozzles, and we'll talk about that in detail in the next lecture. We'll go through what we mean by friction choking. But that's what's happening there. So at that limiting point, you've reached choke condition. You cannot add any additional length to your pipe. And in the next lecture, we're going to talk about this in more detail, and we'll actually draw some ducts so you get a better idea of what I mean when we're traveling along the Fanno line. Okay, so the next lecture is basically entirely focused on Fanno Flow. But yeah, hopefully this was intelligible, and yeah, go and look at some Mach diamonds and know what's going on in your head. And next time we'll talk at length about Fanno or these flows with frictions. So yeah, sounds good. Hope you have a great day, and I'll see you next time.